Okay, so this is the next video in magnetism. This is the fourth video in the magnetism series for regular physics classes, for my regular physics classes. We're going to talk, just review a little bit about magnetism and how that works, and then we're going to talk a little bit more about just magnetism in general with transformers and electricity and kind of how it affects electric charges, because that's kind of what we're dealing with. Is we're getting into magnetic induction, which is how you get electricity from magnets, and that's the gist of how, that's the premise of how we get electricity to be able to use throughout our daily lives. So what we're going to do is first talk a little bit more about magnetism, just review that, and then again, we're going to get into some more details on magnets. So what I've done is I've drawn a magnet here. Most of the time, by the way, magnets are listed north and south. They're dipole or bipolar. They've got two poles. Always, always, always. They at least have two poles. And what happens is a magnet is going to have a magnetic field around that. It's a field force. Okay, magnetism is a field force. Electricity is another field force. Gravitation is another field force. So you have electric force, magnetism, and gravity. All are field forces, which means there's no touching involved. There's no contact required for a force. So you don't have to hit, you don't have to push or pull. Physically, it's done without touching. So that's kind of what we're dealing with here with magnets. And the key thing with a magnet and magnetic fields is that magnetic fields always point from north to south. You always get magnetic fields to point from north to south. So if you were to have iron filings to kind of see what was happening, then we would have these magnetic fields, or these iron filings would kind of orient themselves like the lines I'm drawing. They would line up just like these lines, to where you had them this way or sideways or whatever. Another thing about magnetic fields is that the closer the lines are together, the more concentrated the lines are, the stronger the field is. So it's going to be strongest where you have the most lines. So like here at the poles, okay? Where it's spread further out, you don't get as much of a strength, okay? So if you were to take a compass and line it up, then it would match along with these lines, okay? If that were a real magnet. Kind of another thing, we talked about the other day, or talked about in the other video, is that magnets have, or that the Earth has its own magnetic field. And again, we draw lines from north to south as far as the magnet goes. So we would draw lines like this in this direction to show where this magnetic field is. Okay? And so as far as magnetically, this would be the Earth's south pole. I'm going to go ahead and use black, because red is often used for north. So I use black for south. And then this is the magnetic north pole. Like the needle on a compass usually has a red end or a red point. That's usually north. But we also talked about how if this is the direction that a compass points, if it points toward the north pole, it's pointing towards the north, like the northern area geographically of the Earth, but not necessarily the magnetic north pole. It's actually the magnetic south pole, because it's the north end of a magnet being attracted to that. So that would mean that this compass right here would be pointing towards geographic north, which is magnetic south. Okay? So that means like North America is in here, and this is South America down here, or Europe and Asia up here, and then you have Antarctica down here. So north and south are opposite in magnetic poles than they are geographic poles. So this would be the north geographic right here, which is equal to the south magnetic, okay? And this is the south geographic. And that's a difficult concept to get at first because it's backwards of what you think, but that's what's going on. If you remember that the north needle of a compass always wants to be attracted towards the south pole of a magnet, then that's what's going on. The Earth is one big magnet, and so it has a southern pole in our northern geographic pole. Okay? Alright, so now when it comes to electricity, you can have moving charges also create a magnetic field. Okay, so if this is a wire, right here, okay, and you have current moving in this direction, moving upwards, okay, there's the velocity of the current, it's moving up that wire right there, okay, velocity of the current, I is for current, remember? Okay, then what happens is the magnetic field lines generate around that wire, and the way you figure it out is you take your right hand, okay? There's two right hand rules we're going to talk about today, and you take your right hand and you would wrap it around the wire the direction the current's going. Okay, so if my pin's the wire, then my thumb is going the direction that the current is going. And remember, according to conventional current, it's assuming that it's a proton or a positive charge moving. We know that's actually backwards. Really, it's an electron. But we assumed it was positive a long time ago. That's just kind of what happened, and so everything was made with these rules assuming it was positive. But so so saying conventional current is going this way, that's the velocity of the charge would be this way, then your fingertips, the way they curl, tell you the direction the arrows would go. Your fingertip would be the point of the arrow. So that's giving you the direction that's happening, okay? And so if it was going this way, again, you'd still use your right hand, and that's curling around that way, okay? If it was this way, right hand, curl around that way, okay, if the velocity is going downward. So in our diagram, it's actually like this, all right? And that's known as just one of the right hand rules. This is kind of the first. This is the right hand rule for a current carrying wire. Okay? Alright. Now, one of the neat things that happens with that is that we can take and use that process and we can use it for something called a transformer. Okay? Because if we had this iron ring, or here it's kind of a square box thing, but that's just easier to draw for this purpose. But you have this iron box ring thing, okay? And it has loops of wire. So we have 1, 2, 3, 4, 5, 6, 7. Okay, 7 loops of wire. Alright? What happens is, if you take and you have a battery hooked up here, so we'll say that this is a battery. Okay, so there's our battery, and since I've got a wider end on that, that's the positive side, and that's the negative side. Okay, what happens is it induces a magnetic field there with that ring. Well, if it's connected over here, that means it's going to kind of translate to this side as well. So if you take and you put another loop of wire, okay, so we'll say we've got another loop coming around like this, and say we only put 3 there. What's going to happen is, with fewer loops, it makes the current less, or actually it makes the voltage less. So it reduces it, and that's known as step down. Okay, and this is called a transformer. just like the toy. But this is the transformer that's real, and it's out there helping us get electricity. It allows the high voltage coming from the electric plants or power plants to get to a low enough voltage we can use it in our house. It travels at high voltages, and this allows it to get down. So this would be a step down transformer, and then the power can then be used over here to light up a circuit or whatever. Okay. Now the opposite's true too. You could go from, so here's our battery. Say we only have 3 loops here, or let's say 4. We'll do 4. It doesn't really matter what the number is as long as you use it for your calculations. We'll say 4, and I don't know, we'll put, let's see, 1, 2, 3, 4, 5, 6, 7, 8, we'll do 9. Okay? So here's the battery, and then here's our other circuit. Okay, maybe we even put a parallel in there or something like that. So here's our circuit, and there's our battery. We're going from 4 loops to, what did I say, 9. And that's going to give us a step up transformer, which is going to give us in turn more voltage. It increases the voltage, okay, by the number of loops. Okay, and so it becomes basically a proportion of the number of loops per voltage for the first is equal to the number of loops per voltage for the second. And then you can solve for whatever's missing. If you know the initial voltage of the battery, and you know the number of loops you have, and you know the number of loops here, then you can figure out what's the voltage, or remember, voltage is another name for potential difference. And in dealing with induction and electromagnetic forces, we also call potential difference, it's EMF, or electromotive force. It allows motion, it allows movement, it provides motion for these electrons, eventually allows something to push. And that's kind of how a generator works, or how a motor works. A motor is basically a generator backwards. A generator uses magnets to produce electricity. A motor takes and uses electricity to produce motion through magnets. Okay? The reason that can happen is that while charges are moving, they actually have a force associated with them. Okay? And the way we figure out that force is by using something called the right-hand rule. And we already talked about it dealing with wires, but this is a right-hand rule with a moving positive charge. Okay, right hand deals with positive. And I'm going to let you kind of guess what you would use for negative. In fact, I'm just going to leave you at that on negative, and I want you to ask me in class